Video copy. A very good afternoon to all of you. So in this session, we are going to discuss about the last two units of block 4, and these are unit 16 and unit 17. Unit 16 deals with the linear partial differential equations, and unit 17, the last one, deals with first order partial differential equations. So as you can see in the screen, in that particular unit 16, we have to discuss all about the linear partial differential equation. And in that particular unit, the course structure is like that. We have to discuss about the origin, classification, and solutions of partial differential equations. So, before we are going to discuss about the origin, classification, and solution of first order partial differential equation, I am going for a quick review whatever discussed in our first two units of this block 4, the unit number 14 and unit number 15. In these two units, we have discussed about the simultaneous differential equations, and that has been developed from one parameter or two parameter family of curves and surfaces. And then in the next unit number 15, we have discussed about the total differential equation. That means how we can develop a total differential equation from a one parameter family of surfaces, and then from two parameter family of surfaces, and then what we have discussed already, how can we solve this kind of total differential equations. So now in this session we are moving towards the linear partial differential equations. So let us begin with the origin of first order partial differential equations. In this origin, we have to mainly focus about how to construct a linear first order differential equation from a given equation of one parameter family of curves. Some of the linear partial differential equations examples are given in equation number 1, 2, 3, 4, 5. So as you can see, equation number 1 is a first order partial differential equation because it involves first order partial derivatives ux and ut. Similarly, in the second, third, fourth equation, these are Laplace equation, heat equation, wave equation, or are the linear differential equations, but of order 2. So here, the general form of the partial differential equation has been written in equation number 5, and it contains all the independent variables along with the dependent variables and with its first and second order derivatives, as you can see in equation number 5. So now let us move towards the general aspect of this kind of linear partial differential equation that has been developed from one parameter family of curves. So first, with the help of examples that has been elaborated for one parameter family of curves and two parameter family of curves, then we are going to discuss about the general aspect how we can approach when there is a two parameter family of curves, then how can we develop a linear partial differential equation of first order. So in equation number 14, as you can see, this is a two parameter family of surfaces, and the equation has been represented in the form of capital F with two independent variable x and y and two parameters a and b. So that's why I can say that this is a two parameter family of surfaces. So now first we have to calculate p, that is the partial derivative of f with respect to x, and q, that is partial derivative of capital F with respect to y. But here we have to look at the condition in the form of this 2 by 2 determinant, and in this determinant, as you can see in the first row, that is f of a, f of b, that means partial derivative of f with respect to a parameter, and partial derivative of capital F with respect to b, that is in the first row. And similarly in the second row we are using here the first order derivative with respect to a. Again we are using the first order derivative with respect to x. So similarly in the second row we are using derivative with respect to the parameter as well as derivative with respect to the variables. And here the determinant value should not be 0. So under this condition The equation number 14 and equation number 15 together gives us a differential equation in the form of linear partial differential equation. So here the function, after eliminating the arbitrary parameters a, b, we have a function in the form of f, that is x, y, z, p, q. And here EQ must be the partial derivative with respect to x and with respect to y respectively. And here x and y are the two independent variables in this expression. So the same process has been now elaborated in this example number 2. So let us going to discuss about that example number 2. That means how we can define a linear first order partial differential equation. So here question is to obtain the partial differential equation corresponding to the equation, that is two parameter family of curves. It has been given z square all into 1 plus a cube equals to 8 all cube of ax plus ay plus b. Now, as you can see clearly, this equation contains exactly two parameters, small a and small b. Now we have to eliminate these two parameters by solving the first order partial derivative with respect to x and as well as with respect to a. So here, now we are going to eliminate the parameters a and b, equation number 20 and equation number 21. If we are going to solve these two equations, number 20 and equation number 21, we can easily calculate a relation in the form of equation number 22. So that means the procedure is that first we have to calculate the differentiation, partial differentiation with respect to x and with respect to y. Then we represent it by small p and small q, and then again we have to test that determined value should not be 0, because if the determined value should not be 0, if in that condition we can clearly represent or eliminate the arbitrary constant a and b to find out that this is a form of linear first order partial differential equation. So this is the simple process to find out a first order linear partial differential equation by eliminating the parameter present in the given equation of curves. So now let us move towards page number 71 to discuss the integrating factors in partial differential equation. So look at the general form of partial differential equation. It has been written in the form of capital P is a function of xy dx plus capital Q function of xy dy equals to 0. So clearly this is a total differential equation. So clearly this is a total differential equation. Now we have to determine a function mu xy in such a way that the expression mu p dx plus mu q dy must be an exact differential. And if that will be exact differential, we will be able to represent in the form of del by del y mu p equals to del by del x equals to mu q. So once we can represent in that particular form, it is very easy to integrate and to find the solutions of the corresponding differential equation. So here the integrating factor is also useful in partial differential equation to find out the solution of linear first order partial differential equation. So now look at one of the Euler's equations for homogeneous functions. So as we have already discussed about the homogeneous function in unit 7 of block 2, and according to the definition of homogeneous function of independent variable x and y of degree n, the general expression is like that: f of lambda x lambda y equals to lambda to the power n f of xy, and here lambda is any constant must be positive real number. So in that case, if we are using a relation in the form of z equals to f of xy, and f of xy is a function of x and y of degree n. So that's why this kind of functions or relation will leads to a differential equation in the form of Euler's theorem by using the first order partial derivative with respect to the independent variable x and y. So here we can represent x fx plus y fy equals to nf. So this particular relation is known as Euler's theorem or Euler's first order differential equation. So now let us move towards the next page. So on page number 74. So in page number 74, we have to focus on the classification of the first order partial differential equation. So now, according to the nature of the first order partial differential equation, we can now categorize into different types of first order partial differential equation. So look at the expression here. It has been represented in the form of small f x y z p q. So here let us focus on the independent variables. So here x and y are two independent variables. Z is a function of x and y, and p is a partial derivative of z with respect to x, and q is also partial derivative of z with respect to y. So these are the notations we are using inside the functions. So now, whenever we can say this kind of function is a linear differential equation. So your condition given that if f is linear in each of the variables z, p, and q, and the coefficient of these variables are the functions of only independent variables x and y. That means the power of the variables z, p, q must be linear, and the coefficient of all these variables z, p, and q must be a function of independent variable x and y only. So now, according to that basic idea, we can represent the general form of linear first order partial differential equation in the following form, and it has been written in equation number 47. So in equation number 47, the first term is Pxy small p, Qxy small q, capital R xy, z equals to hxy. So clearly here capital P, Q, R, H are the functions only of the independent variable x and y. And the equation is clearly a non-homogeneous first order partial differential equation in the form of linear because hxy is not equals to 0. So whenever hxy equals to 0, the equation will be said to as a homogeneous linear first order partial differential equation. So this is the first category of the linear first order partial differential equation. Now look at the second kind, and that is known as semi-linear first order partial differential equation. So semi-linear, that means look at the form represent in equation number 51. So in equation number 51, in the right hand side of the function, that is r, is a function of three variables x, y, and z. But the other two functions, capital P and capital 2, both are the functions of two independent variables x and y. So that's why this kind of expression, the functions are known as semi-linear partial differential equation of first order. Some of the examples are given in equation number 52, 53, and 54. And clearly you can see in the right hand side of the function that does not contain p or q is a function of x, y, and z. So that's why these kinds of equations are known as semi-linear partial differential equation of first order. So now let us move to the third kind of first order partial differential equation. And here, if we focus on the equation number 55, and that has been defined capital P, capital Q, and capital R. All the three functions are the function in the form of x, y, and z. That means all the three variables are present x, y, and z. So whenever we find this kind of expression, and such equations are linear in their highest order derivative, and there must be small p, small q. That means they are the first order partial derivative with respect to x and with respect to q. So whenever the coefficient of small p, small q, and in the right hand side of the expression must be in the form of the function x, y, and z, then in that case the equation should be quasi-linear partial differential equation of first order. So the same example has been given in equation number 56, 57, and 58. In these three equations, all the equations are given in the form of first order partial differential equation. But if we focus in all the coefficients of small p, small q, and capital R, all are containing the functions in the form of x, y, and z. So that's why clearly you can say that this kind of equations are known as quasi-linear first order partial differential equation. So now, till now we have discussed three kind of first order partial differential equation. First one is linear, then semi-linear, third one is quasi-linear. So now, whenever a differential equation or first order differential equation does not satisfy in these three categories, that means linear or semi-linear or quasi-linear, then obviously it will be in the form of non-linear partial differential equation of first order. And it has been written in equation number 59 and equation number 60. If we focus on these two equations, we will clearly find these two equations we cannot express in the form of linear or semi-linear or quasi-linear partial differential equation. So that's why these kinds of equations are known as nonlinear partial differential equation of first order. So till now we have discussed about the origin and classification of first order partial differential equations, and in classification we majorly focus on the three types of partial differential equation of first order. First one is linear, second one is semi-linear, third one is quasi-linear. And if a partial differential equation is none of these three kind, then it must be a non-linear partial differential equation of first order. So after discussing that classification of linear partial differential equation of first order, we are moving towards the phase number 76 to discuss about the solution procedure and what are the different types of solution exist in this first order partial differential equations. So here some examples has been given to discuss about the solution procedure, but let us first know what are the different kinds of solutions are possible when we are going to solve this kind of first order partial differential equation, whether it may be in linear or quasi-linear or semi-linear partial differential equation. So here the solutions are also known as integrals, so that's why it has been written here classification of integrals, or also you can say that classification of solutions. So first type of solution is complete integral, or it may be known as complete solution. So here a two parameter family of solution, that is in 64. So here we have represent small z equals to capital F is a function of x, y, a, b is called a complete integral of the equation number 18. That means if that particular two parameter family of surfaces satisfy partial differential equation, then you can say that it must be a solution, and it is known as complete solution to the partial differential equation because it contains two parameters a and b. Now let us know about the general integral and general solution to the partial differential equation of first order. So here we have to substitute small b equals to b is a function of a. That means if we are able to find a relation and we can express b in terms of small a in the functions of a, then the solutions will be looks in that particular form, that is x, y, a, and b is a function of a. So that particular expression clearly can see that this is a one parameter family of solutions of the equation number 18. So that this kind of equations are known as general integral and general solution to the partial differential equation of first order, and that has been more generally expressed in the form of xy, that is xy independent variable, a is a function of xy, again b is a function of a as well as a is a function of x and y. So these are the first two kinds of solutions possible in linear first order partial differentiation. So now the last one, that is particular solution. So now whenever we are able to assign some particular value, whenever we are able to assign some particular value in place of these arbitrary constant or parameters b, in place of this arbitrary function b, then that kind of solutions are known as particular solution to the partial differential equation of first order. So that means the particular solutions can be obtained from the solution of general solution or general integral. It cannot be directly obtained from the partial differential equation. Now, the third kind of solutions are singular integral. So here, singular integral can be obtained from the solution or general solution of the partial differential equation along with this set of equation. Look at the equation or set of equation represented in equation number 69. In equation number 69, first relation is the complete solution or complete integral of the partial differential equation. Second one is the partial derivative of the first one with respect to a, where equating to 0. And third one is partial derivative of f with respect to b and equating to 0. Now, if we are going to solve this set of three equations, then that will gives us a solution that is known as singular integral to the partial differential equation, and that has been discussed in this expression here. So here it has been taken that small z is equals to x plus by plus a plus b minus ab equals to a function in the form of capital F, and that is a complete integral of a partial differential equation. It has been written the differential equation is px plus py plus p plus q minus pq. So that particular expression is the two parameter family of planes with the complete integral of the equation represented in equation number 70. So now let us know how we can find the singular solution from this set of solution. So here z has been represented. We have calculated partial derivative of f with respect to a then equating to 0. We have a relation x plus 1 equals to b. Similarly, we are calculating partial derivative of f with respect to b equating to 0. By solving this, we will get y plus 1 equals to a. So that means we can now assign the value of a equals to y plus 1 and the value of b equals to x plus 1 in place of the parameter ab in the complete integral. So here, as you can see clearly, the parameter a and b has been replaced by the relation a equal to y plus 1 and b equals to x plus 1. So after replacing, the resultant relation of the function in the form of xy is known as the singular solution to the partial differential equation. So this is the simple procedure to know about the singular solution of partial differential equation of first order. So we have discussed about the classification of integrals or classification of solutions in partial differential equation, and here the first kind of solution or integral is complete integral, then general integral, then we discuss about the particular integral, and finally we discuss about the singular integral of the partial differential equation of first order. Now the fourth kind is special integral obtained from the first order partial differential equations, and here as you can see, special integrals are obtained in some exceptional cases. So here that cannot be obtained from the complete integral or general integral or particular integral. So that can be in some exception we will able to get special integral from the first order partial differential equations by eliminating the parameters a or b present in the differential equation. So here one of the examples given in example number 8, the family of planes, that means complete integral is given. Now we are differentiating with respect to x and y. We are able to eliminate the parameters a and b in terms of pq. So this expression, which is the partial differential equation of the family of planes, and this is clearly a first order linear partial differential equation. So now we are eliminating by calculating the first order partial derivative with respect to parameter a and parameter b equating to 0. We have a relation in the form of a and b in the form of xy. That means a equal to minus x by 2 and b equals to minus y by 2. And finally, we are substituting back these two values. We will be able to find a solution in the form of singular solution of the linear first order partial differential equation. So after discussing all these expression, we are going to discuss about the last unit, that is unit number 17, that is all about the first order partial differential equations, that deals with the solutions of Lagrange method and Charpit method to find out the solution of linear and non-linear partial differential equation of first order. So let us move to the page number 89. So as you can see in page number 89, we are now proposing to discuss about the first order partial differential equations. So here in the first order partial differential equation, we have to cover the linear equations of first order and then nonlinear equations of first order. Then how can we know the system of first order equations are compatible or not? Because if the system of first order equations are compatible, then we can easily solve by using a systematical procedure. But if it is not compatible, then we have to use the Charpit's method to find out the solution. And then finally, we're going to discuss about some standard forms of first order partial differential equation to find its solutions. So let us move towards the linear equation of first order partial differential equation in page number 90. In page number 90, we mainly focus about the expression of linear equation of first order partial differential equation. So here we consider the quasi-linear first order partial differential equation. And as we have already discussed about the general form of quasi-linear first order partial differential equation, and in these kind of equations, the coefficient of small p and small q, and in the right hand side of the function, that means capital P, capital Q, and capital Y, must be the functions of x, y, and z, but not involving p or q. So these kind of equations are known as quasi-linear first order partial differential equation. So now this kind of equations are also known as Lagrange equation. Now we are going to discuss the general solution or general integral of this kind of quasi-linear or Lagrange equation of partial differential equation of first order in the following theorem. So theorem number 1 suggests us to find the general integral or general solution of this kind of Lagrange equation, or that is also known as quasi-linear partial differential equation of first order. So
हमरो जाने पा जातो
बोला तू होतो để cái भांग भांगुना भांगुना गुना पके
नहीं वो कोरोना हाथ पर टाउन पर बोले पोला सब दिन आछे गाला ওই যে পলাশ গান লাগো ওদনা আছে কাল পলাশ কাল ওদের বলা আছে বলে পলাশ মিলে আইগো মিলে মিলে পলাশ ওদনা আছে বসিহান মাস বিতে পলাশ ঠিক আছে বাবু কার আছে হ্যাঁ হ্যাঁ কত হ্যাঁ
in the form of ZPQ. Now, let us know we are calculating partial derivative with respect to Z, then with respect to E, and with respect to Q, and then we are solving the last two expression to find out the value of Q equals to 0 or Q equals to A plus 1 by AZ. Now, if we are choosing the value of Q equals to 0, we are able to get the value of P equals to 0. Now, if we will get the value of Q and value of P in terms of parameter and other variables Z, then we can very easily substitute these values of small p and small q in the total differentiation form, that is dz equal to pdx plus udy, and after substituting the value of small p and small q that was obtained earlier, we can easily integrate both sides to get the solution that will be the complete integral of the differential equation of first order. So these are the different types of differential equations that can be easily solved by using the Charpit's auxiliary equation as we discussed type 1 and 3. Now, in this session, today we are going to end the session